Okay, it's really a great pleasure being here. And as I listen to talks after talks after talk, I really found that I'm connecting to all these guys. Because at a very general level, we're all trying to explore the world and try to learn something new. And what I want to tell you today is one of those things that we are doing at Cardiff. But the story really goes back to almost 4 millennium. In fact, it's a little more than 4 millennium, 400 years. Astronomy began with the invention of the optical telescope. And 2009, we celebrated the International Year of Astronomy, celebrating what Galileo did 400 years ago. And here is Galileo showing off his telescope to the Venetian authorities. Actually, it was Hans Lippershey of Amsterdam in 1608 who discovered the telescope, but Galileo only had heard about it. But this guy in Amsterdam really did not put telescope to any great use. Galileo heard about it, he constructed a telescope, and what does he do? He points it to Jupiter about 402 years ago. And our view of the universe since that day has completely changed. From what was actually a geocentric view of the universe, by just observing that there were planets going around Jupiter, Galileo was able to convince himself and many other people that actually the geocentric view of the universe is completely wrong. But that particular observation that Galileo did was using optical telescope, but the optical window is really only a very small window of the electromagnetic spectrum. This is the electromagnetic spectrum, which shows you many different frequencies, starting from very small scale, smaller than the atom, the size of the nucleus. This is 400 nanometers here. And as you go to longer and longer and longer wavelengths, the wavelength of light could be as much as tens of meters, hundreds of meters. Those are the radio waves. There are microwaves and so on. The world today. It just fell. Okay. The world today we use not just optical telescopes, but radio telescopes, microwaves, infrared, ultraviolet, X-rays. All these different windows of observation tells us that the universe actually consists of mostly dark things, dark matter, and what we have come to call dark energy, but we have absolutely no clue what that is. So what my talk is going to be is to tell you another window of observation. This is the whole electromagnetic window, but I want to tell you the story of a new window of observation, what is called the gravitational window, which will open a new way of looking at the universe. And we'll be using gravitational waves to observe the universe, and I want to tell you what this new window is all about. It begins with Einstein, about 100 years ago, who told us about E equal to mc squared, but he also told us that space and time cannot really be separate. They are together, and space and time are merged together to form a space-time curvature, and actually planets like Earth go around the sun not because of some mysterious force, because the space-time is itself curved. And here in this cartoon, I'm showing moon going around the Earth, and it's because Earth around itself has caused a curvature in which the moon is going around in the straightest possible path, but it appears to us as though in a curved path because we can't see the curvature of space and time. But hopefully that will change if we can see the ripples that are caused by the moving object, and that is what we are actually trying to observe. For instance, if you have two very massive objects, very compact objects, more precisely, like black holes, that are going around each other, then they will actually create a ripple in the very fabric of space-time, which goes outside, from their source at the speed of light. And we want to be able to detect ripples of space-time curvature as they go out. How can we do it? Well, first of all, let's ask ourselves whether these gravitational waves exist or not. And the story goes back to only about a quarter of a decade, slightly longer, 1974. Russell Hulse and Joe Taylor in America actually detected the first what is called a binary pulsar, in which there are two neutron stars. They are going around each other. Neutron stars could appear to us what are called pulsars, in which radio waves are emanating. And whenever we are in the path of radio beam, we will observe it as emitting radio pulses frequently. These stars are only of the size of something like a big city like London, 10, 15, 20 kilometers. But yet, they contain about 1 solar mass within that region. So 1 spoon of this matter will probably weigh something like 10 million tons. So that's how they are heavy, but they are really flying wheels in space, and they are going around so rapidly and maintaining their clock, their ticks so accurately that we can time the orbit. And Hulse and Taylor did that, and they concluded that these two objects are actually not maintaining their orbit as predicted by Newton. Newton would have thought that they should go around each other like that forever, but they actually measured that this orbital period, which was 7.5 hours, was changing ever so lightly. It was changing only by about 10 microseconds per year. We really don't care about that kind of small time that elapses. But even so, but because these are extremely precise clocks, Hulse and Taylor were actually be able to measure the change in the period, orbital period, and that is really due to gravitational waves, it turns out. And today we know that Einstein's theory of gravity, which predicts the emission of gravitational waves and the merging of this binary neutron stars, is completely consistent with observations. And Hulse and Taylor in 1993 were awarded the Nobel Prize. So once the Nobel Prize is awarded, the funding councils get very enthusiastic to support the project and to directly observe gravitational waves instead of this indirect observations. But we have to tell them, what are we going to do? How are we going to construct observatories that can look at these gravitational waves coming from these binary neutron stars? This is what gravitational waves do. This is a little technical, but I'm not going to spend too much of time. If you take a ring of particles, which are completely free, they are not experiencing any other force, and gravitational waves are going into the screen, then the ring gets deformed into this elliptical shape over 1/4 of the period, back to that white circle, and then over the next quarter, it will get deformed into that green ring, and so on and so forth. And this happens due to one kind of polarization called plus polarization. The cross polarization of gravitational waves will cause a similar pattern. It's not very, very different, except that it is rotated by 45 degrees. It's very similar to the way electromagnetic antennas work, like radio antennas. They are just moving the charges, but in this, as they pass through a material. But in this case, anything that is in the path of gravitational waves will get tidally deformed, as shown in this graph here. Now, this is what we use. Instead of these free particles here in these portions, we hang a mirror, as shown in this next diagram here. So you put 2 mirrors on this circle that we were looking at, and you shine a laser beam that goes into these 2 different directions, and they are reflected back from those end mirrors there. We form a cavity too, but that's just a technical detail. But the whole point is that the light goes back and forth, and it interferes here and detected in this photodetector. If there is no gravitational wave passing, then there is no light here. That's the way these things are arranged. All the lights exits towards the laser. And when a gravitational wave passes, one of the mirrors comes towards the beam splitter, the other mirror moves away during 1/4 of the gravitational wave period, and there'll be some light seen in the photodetector. So in this way, one can detect gravitational waves. So over the past about 20 years or so, enormous effort has gone into building a worldwide network of gravitational waves. And this map of the world shows you where they are. There are 2 in United States with 4-kilometer long arms. Longer the arms, it turns out it is better for us. And there are 2 in Europe, one in Pisa, where Galileo was doing his work. He was born there. Very rightly, we have gone back to Italy in Galileo to conduct one of the biggest experiments of this century. And also our own GEO 600. It's only 600 meter, as opposed to the 4-kilometer in the US and 3 kilometers in Virgo. The British-German project turns out to be only about 600 meters. We are somewhat poor in this direction, but it turns out that the best technology actually comes out from the British-German project, and the other projects are also benefiting from that. There is a plan currently underway to build a detector in Japan, and the new kid on the block is India. And our US colleagues want to transfer one of the interferometers, these 4-kilometer interferometers, to India. This is currently being negotiated with the higher-up politicians in India, and we are hopeful that it will come through. So here is the US Hanford site, which currently houses 2 interferometers in the same vacuum tube, and we are hoping one of them will be shipped to India in order to create a very big global network so that we can triangulate sources on the sky. This is the Livingston site. You can see the difference in the vegetation. The first one is a nuclear site, whereas there is a lot of forest here and logging and so on. This is our own British-German GEO 600, where we have a 600-kilometer. 600-kilometer arm detector. And then this is the French-Italian beautiful Alps mountain in the distance there. And finally, just the artist's impression of what the LCGT, the Japanese detector, looks like. The current status is that after successful data taking with initial design sensitivity, these detectors are being upgraded. And when they are upgraded, they will be 10 times more sensitive than what they are today. And in fact, this upgrade should have taken back in 2006, 2007. But because of war in Iraq and Afghanistan and so on, the Bush government delayed funding. And finally, with Bush gone and Barack Obama in, we have finally funding to do this project. And when these advanced detectors begin operation in about 5 years, they will start to hopefully make the first direct detection of gravitational waves. So this picture tells you what those advanced detectors are able to do. The initial detectors which completed their runs were only able to see the local universe. We say local universe for something that is about within 30 million light years. That's our backyard. So we were only able to see within that region. But when advanced detectors are able to observe the universe, they will see out to thousands of millions of light years. That is giga light years. And for comparison here, that's 100 million light years. That scale here is 100 million light years. So advanced detectors will really start to observe the cosmological universe. And the plan also looks extremely good for future. We already started thinking about building detectors underground, just like our Japanese colleagues here in Europe. 10-kilometer tunnels, a triangular detector to observe. And very rightly, it is called the Einstein telescope. And it will be an underground observatory to watch the gravitational waves in the universe, and also a spatial detector. I want to say a few words about what kind of gravitational wave, what are the different gravitational wave sources. As I mentioned right in the beginning, these are ripples in the space-time curvature. Space-time is extremely rigid. In order to cause any ripples, you first of all need enormous amount of energy, and only things that can do them are really things like black holes. And black holes are ubiquitous. They are there everywhere. And that's the reason why we are hopeful that one day when we can see collisions of black holes, as depicted in this picture, there are 2 black holes in the center of a nearby galaxy, and they're orbiting around each other. And we know that they will coalesce within Hubble time, which is about 10 billion years. We know one object that's going to coalesce within the Hubble time, but there must be many other, millions and billions of these objects dispersed throughout the universe, which will coalesce. So, but black holes also come in many different sizes. There are stellar mass black holes, mass of the sun, but there are also millions of solar mass black holes. And here is an example. I think I'm pressing the wrong button all the time in my excitement. And here is a wonderful observation. This is not a movie. This is based on real observations of the center of our galaxy. Look at all these different stars. In order to guide your eye, the animators had to put a circle to show there is nothing around which all these stars near the center of the galaxy are moving around. And this particular star is a very important star because that tells us precisely what is the mass of this object here, and it's about 4 million solar masses. It's a 4 million solar mass at the center right at the center of the Milky Way, and that's what could be a source of gravitational waves. And colliding black holes are, in fact, the most luminous objects that you can ever see. Here in this movie produced by Caltech Cornell Group, you see two black holes going around each other. As they go around each other, they produce these gravitational waves. And when they collide, they emit more energy per unit time than all the stars in all the galaxies in the world, the most luminous objects. And those are the kind of things that we hope to observe. And here is a soundbite. Oh, I don't think... that tells you that the two black holes merged together. Because you did not hear anything after that, right? And they formed a single black hole, and that is the way we're going to observe these black holes. And here is the two binary neutron stars. I mean, it's a two neutron stars going around each other, and when they collide, it's a catastrophic event which might produce gamma rays that are observable when the universe was still in its infancy, basically, right? At redshifts of 2 to 3 to 4 in our third generation detectors, you can see the space-time curvature. This guy was quite intelligent. I mean, I couldn't see the space-time curvature moving around, but the guy who created this was able to create the ripples in the curvature of space-time. And I think the big action in the universe is really, if you see the Hubble Space Telescope pretty pictures, what you see is galaxies are always interacting. They're colliding with each other. They're merging and they're eating with each other and so on. And this is a big thing for gravitational wave detectors because these big black holes, they grow by accreting not only gas and dust, but also each other. There's a lot of cannibalism going on here. And you can see after the galaxies merge, the two black holes are still far apart, but they come together and finally they collide and they merge with each other, emitting the most spectacular event, not in optical, but in the gravitational window. And our interferometer detectors will be able to catch and observe events events of this kind far into the early part of the universe. And here is another example of a soundbite in which a tiny black hole is being gobbled up by a big black hole. You can see complicated orbit of the small black hole. Sorry, I'll be through in a few minutes. So that's the small black hole getting into the big black hole, and the small black hole actually was tracing out the entire space-time region of the big black hole, and we should be able to get a sample of that. I think I'm going to skip this slide and tell you that really the most important thing, the holy grail of the gravitational astronomy, could be observing the very earliest moments of creation itself, by creation of the big universe. We believe that the universe originated about 12 billion years ago in a Big Bang, and our view of that universe comes from what is called the cosmic microwave background, which began its journey freely only about 400,000 years after the universe was born. But actually, using the gravitational window, we can see tiny fraction of a second after the birth of the universe, and this is 0.0000, etc., 20 times. After that, there's a 1. Such a tiny fraction of a second after the universe was born, we should be able to see one day with gravitational wave observations. I want to just point out a couple of outreach activities that we have taken part in. This is the Einstein at home. It is a Sathya at home kind of activity where you, general public, can take part in gravitational wave searches. So we can use the based compute cycles on your computers when you're not using it, when it is lazy. You can download a simple program, look for Einstein at home. You should be able to download it. And also, there is a game called Black Hole Hunter, which should be useful, which would be a fun play. I mean, somebody was, Ben was talking about play. That would be a good thing. I want to end on a small note about, why should we do fundamental physics? What is the point? The point is that I think we as humans are really exploratory. We explore things. But we do pure science not because it is of utility. It's not utilitarian, but it's because because it increases our knowledge. And here in this, you have this GPS satellites going around. You might have seen some numbers there. These GPS satellites, John, you could not have crossed the Atlantic and taken your journey without the GPS, I believe. I mean, I asked you how useful GPS was. Probably not a lot. But that GPS would not have worked within a few minutes if it were not for general relativity and Einstein's theory of gravity correcting it all the time. So I think fundamental physics and pure science is very, very important. It is exploratory in nature, and it is something that makes us what we are. Thank you very much.